Welcome back to Valiant PE. Today's topic, eccentrically loaded bolted joints. An example. Let's go. Okay, this example is going to be a little harder than the last example we looked at. You can tell we've got a load here that's at an angle, unlike what we've seen in other examples. And we've got an off-center load, so it's going to be challenging, but if we can solve this problem, we can solve any eccentrically loaded bolted joint problem that we're going to encounter on the exam. So let's do our pre-question ritual and get to it. Take a deep breath. Read the question slowly. A steel bracket is bolted to a steel beam using 4 M20 by 2.5 class 12.9 bolts. The bracket is subjected to a 117,393 pounds force load as shown. Determine the factor of safety against proof strength in the most heavily stressed bolt. And immediately we write down what we're solving for, which is going to be a factor of safety or an end value. Okay, one trick I like to do, especially when we're dealing with stress, is think about what types of stress we could possibly solve for and eliminate them, the ones that we know we don't need, so we are only spending our precious time on solving what we need to solve. So axial, we don't have any information about bolt preload or any information about a depth here, so we're probably not working with a tensile stress area issue, probably not doing any bolt tensile stress here. Bending stress, no information given about the beam as far as geometry goes, so we're probably not going to be able to solve for an I value, so no MC over I, no bending stress. Shear stress, we see we've got the load is at least has some component that is perpendicular to the axis of these bolts, so we definitely have shear planes in play here, so we probably have shear. Torsional, this force is probably going to want to make this bolt group twist or rotate in that direction. So yeah, we probably have something torsional related. Transverse, since we're not in bending and we don't have a very short beam, we don't have any induced transverse shear stress. And then bearing stress, we're not given any information about, say a distance here or anything like that. So I don't think we have a tear out type problem. I think what we have here, based on this, is we've got an eccentrically loaded bolted joint. That's really good for us. We know how to solve these. We have a problem solving procedure. Let's get to it. Okay, step 1, find the centroid. This is easy. We've been given all this geometric information already, but you can see we've got an axis of symmetry, so that's very good, symmetric there. About that axis. This value here, 5.374 inches, that's given from the problem. Let's add these together. And the distance here is 11.284 inches. Okay, remember, when working with critical fastener, we're either going to be, either one of these two bolts is going to be our critical bolt. And we know that. And so we definitely need this distance here in order to solve for our sum of R squared terms. Okay, step 2, draw the force vectors. Before I draw the vectors, let's take a look at the load here. It's given in the problem statement that this is a 32-degree angle. So let's go ahead and roughly break this down into its X and its Y components. I'll put X in blue and Y in red. We'll call this Fy, and we'll call this Fx. And let's just go ahead and solve for the XY components. You have to do a little bit of trig here. This is probably more complicated than you're going to see on an exam. I don't think they're going to really want you to spend this much time doing trig, although you could probably knock this out in 6 minutes. It would definitely be a challenge. Okay, so we've got our load value, we've got a angle value, so let's solve for the X and Y components. So this value here is 117,393 times cosine 32, That's going to equal 99,555 pounds force. Let's go in here and do the y. 117,393 sine of 32. That's going to give us 62,209 pounds force. Okay, so we've got these values here, these components here. Now, remember, our governing formula here, total force, is equal to the vector sum of primary shear force plus secondary shear force. Let's treat primary first. This is by far the simplest. And we're actually going to have two components here. So let's start with our Fx value. We know this value, but let's draw the vectors. How does it look at the bolts? Well, remember that primary shear is always going to be split equally between the fasteners. That's one of the assumptions here. And we're going to call this Fx prime. Remember, we're using Fx. We're dividing this value equally between 4 bolts, and we're going to call it Fx prime. Now we're going to do the same thing with Fy. And remember, these act in the same direction as the applied force, and we're going to call this Fy prime. So these are the primary shear vectors. They're very easy to solve. We can knock these out instantly. That's one of our tricks here. Remember, we always want to draw force vectors first, because that's going to help us see which fastener is going to be the critical one. Now let's come back to do the secondary shear. Let's treat our Fx value as the first one. So that's our bolt centroid. Which direction is this force going to make this device rotate? It's going to look like that. So we know that for bolts over here, the force vector is going to be down, and bolts over here, the force vector is going to be up. So let's draw those. Now, remember that the critical fastener is going to be farthest away from the bolt group centroid, which is right here. Now, I've drawn these in difference in magnitude. You'll see why as we compute the secondary shear term, but I just want you to see these don't equal. They're not the same value. Now, they're symmetric, but they're not the same value. We're going to call that X double prime. And now we're going to do the same thing for Fy. It's going to want to make the bolt group rotate that way. So shear forces over here are going to be down. Shear forces here are going to be up. Let's draw them. Now the magnitude, or how I'm drawing them here, is not really as important as their solved values. We will get to that in just a moment. We are going to call that Fy double prime. Okay, good. So we can easily see, let's just label these A, B, C, and D. We can easily see that either A or D has the most resultant vectors. We don't know which one, what these values are yet. We don't know which one's critical, but we know it's A or D. So now let's go to the next step and actually compute these values. Step 4, vector summation. Got that backwards, sorry. Step 3, compute primary and secondary shear forces. Remember, this is our governing equation here. And remember that F prime is equal to F over N, and F double prime is equal to F times eccentricity times radius to the investigated fastener times the sum of all of our R squared terms. Let's handle these first. Remember, we have 2 of them. Remember, we've got an Fx and an Fy prime. We're going to knock those out first. Fx prime is equal to 99,555 pounds force divided by 4 bolts, 24,889 pounds force each. And Fy prime is equal to 62,209 pounds force divided by 4 bolts, 15,552 pounds force each. So good, we know these values. We're going to come write them in a moment, but we know what these are. Now, let's go back to this term. This is going to be a fair amount of computation. This is going to be the hardest term to figure out. So let's do that first. Our sum of our squared terms. Now remember, we're going to write the radius from the bolt group centroid. We're going to draw the radius for the bolt group centroid of each one of these. Let's start with fastener A. Some of this information was given. So we've given all of our geometric information, our dimensional information from the problem statement, which is what you should have on an exam. They're not going to stiff you on this. There shouldn't be any surprises, but it's fairly simple to write out. So let's go ahead and write it out. This guy is A. That's B, C, D. 5.374 inches plus 5.91 inches equals 11.284 inches. We've already seen that. We've already solved that, and we know that D is going to be the same. Okay. Now B and C are also going to be the same, but a little bit simpler. Just going to be this value here. So 5.91 inches, 5.91 inches, easy. Okay, great. But remember, we have to have R squared terms. So we're going to square each one of these. Let's compute those real fast. 27.3 inches squared. 34.9 inches squared. Now, we're going to sum those. Excellent. That's the hardest part of this whole deal. Now, I wanted us to walk through an example like this so that we could see. If you have a bolt group where the radii to certain fasteners are greater than others, you have to do this step of summing for your R squared terms. It's a lot. Most likely you're not going to have this on an exam, but if you can do this and if you understand this, you can do any of these fastener groups and shear problems. If you can do this, you're going to have no trouble. So let's come over here and solve for fx double prime and fy double prime. Remember our formula, FERI over sum of R squared. F, which one is F? Okay, Fx here. We're going to be solving for this guy. We know what it is. It's 99,555. 99,555 pounds force. Now, times E. What is E? Okay. E is our eccentricity. That's our Fx vector. Again, dimensional information given, 7.15 inches from the height of the bolt group, the distance from the bolt group centroid to the height of this vector. So it's good for us. We know that. All right, let's throw it into our equation. 7.15 inches, that's our eccentricity. And now Ri. Remember, we're looking at either A or D as a critical fastener, so we're using the radius for A or D. Doesn't matter. They're the same, 11.284 inches. All over our R squared term, which we just solved for, 324.4 inches squared. Let's just double check our units. Are we going to get pounds force? Yes. 24,760 pounds force. Okay. Now we're going to quickly do the same thing for our Fy term. Remember, that's this force. What is its eccentricity? That's going to be the distance from the bolt group centroid to this vector, which is 1.182 inches, again, given. So, 62,209 pounds force times 1.182 inches times 11.284 inches, 324.4 inches squared. All right, great. And that's going to equal 2,558 pounds force. Now, all that work, what does it get us? Now, step 4, vector summation. This is where it all comes together. Let's draw out our force vectors, which we've already drawn once. These are our primary shear vectors. This is going to be for A. These are our secondary shear vectors. Remember, we've also got D. These two are equal. Now these go in the opposite direction. All right, now let's write some values here. We've already solved for these. 24,899 or 889. 24,760. These are in pounds force. 2,558. Now, if you look at A and D, you know the values are the same. You can easily see that these two are going to sum, and they're going to make a much bigger vector. Here, they're working against each other, so we know just by looking at this, fastener A is our critical fastener. So, let's write Pythagorean theorem and solve for our resultant force value. We're going to do X pounds force squared. Now we're going to sum all those Y values. 15,552 plus 24,760. Oops, it's a minus 2,558 squared. What does this come to? 45,220 pounds force. So we know this value here. Excellent. Okay, so that's only half the battle. We now have to compute bolt shear stress and factor of safety. Remember, our shear stress formula, generic shear stress formula, is V over A. We're going to rewrite that in our terms here, which is our total force vector times over 2 of the cross-sectional area of the bolt. Now, why am I saying 2 times A rather than just A? We made an assumption by looking at this diagram that we're in double shear here. This bolt goes all the way through, and we've got a shear plane here and a shear plane there. So, cross-sectional area of the bolt times 2 gives us what we're looking for. Now, I've been using inches and pounds force because we're solving for a factor of safety. No one told me what units I had to use. But when it comes to calculating the cross-sectional area of the bolt, let's rewrite this. We've been given a millimeter dimension. Okay, 2 times pi over 4. Well, what's my D? From table 1 of our reference manual, we see that a millimeter, 1 inch is 25.4 millimeters. So we're canceling there. We end up at 20 over 25.4, and this is our bolt diameter. Now again, this is metric, not coarse or fine thread standard, so I'm going to use nominal diameter and make an assumption there. As far as I can tell, as best as I've searched, there is no minor diameter information given for metric bolts, so we're going to use nominal. Compute our shear area here, and we end up with, as a shear stress, 46,479 pounds force over inches squared. Good. So that's our bolt shear stress. Excellent. Now last step, factor of safety. Okay. What is our maximum allowable shear stress? Well, we know from distortion energy, and we were given a key term here, proof strength. So proof strength is given in a table. We can look that up in our reference manual. But for right now, the generic shear stress formula for distortion energy criteria, again, an assumption I'm making, not maximum shear stress, distortion energy. We've got 0.577 times the proof strength. Well, what is our proof strength? Given in our manual on page 201, depending on what version of the manual you have. This is 970 megapascals. So I'm going to go ahead and convert. We see that 970 megapascals, or a megapascal, is equal to 140.038 psi in 1 megapascal. Cancel our units. We end up with 140,687 psi. Great. Let's rewrite this. 0.577 times 140,687 psi. And that means it gives us our maximum allowable shear stress as 81,176 psi. Last step, guys. What's our factor of safety for proof strength? 81,176, wow, psi over. So that's our max allowable shear stress over our induced shear stress, 46,479 psi. Cancels. 1.75. There it is. So, again, if you can solve this example, you can solve any fastener grouping shear question you're going to get on this exam. We only made a couple of key assumptions: distortion energy, nominal diameter, double shear. I think those are reasonable assumptions. Again, you'll be able to verify those by looking at your multiple choice answers. Sometimes you can eliminate answers real quickly and validate your assumptions, but if we can do this, we can do anything that this exam throws at us, and that's what this channel is all about. So remember, guys, you don't have to be a genius to pass this exam. Thanks for watching.